Water, the most abundant natural resource on Earth. But beyond drinking, irrigation, or transportation, it holds power, immense power. In this episode, we take you inside the colossal world of hydroelectric energy, where millions of kilowatts are harvested each day from flowing water. From massive dams to precision turbines, from mountain reservoirs to electric grids powering cities, this is how hydroelectric power is made. Coming up, we'll dive deep into how gravity, water, and engineering come together to generate clean, renewable electricity at scale. Hydroelectric power, also known as hydropower, is the process of generating electricity using the energy of moving water. The principle is simple. Gravity pulls water downhill. That motion can turn turbines, just like wind spins a windmill. The key concept is potential energy. When water is stored at a high elevation, it has stored energy due to gravity. When it flows downward, this energy becomes kinetic, motion, which we can convert into electricity. The earliest versions of this idea powered water wheels in ancient civilizations. Today, it powers entire countries. At the heart of many hydroelectric systems is the dam. Built across a river, a dam creates a reservoir by holding back water and controlling its flow. One of the world's largest dams, the Three Gorges Dam in China, spans more than 2 kilometers across the Yangtze River. It can generate over 22,000 megawatts, enough to power millions of homes. The dam has multiple gates that control how much water is released. Behind it, the reservoir stores billions of gallons of water, like a giant battery waiting to be discharged. Engineers must carefully manage this water, especially during rainy seasons. Too much flow can flood communities downstream. Too little, and the turbines can't generate enough electricity. Once water is released, it travels down large pipes called penstocks. These pipes funnel water from the reservoir to the turbines below, often dropping hundreds of meters in elevation. The greater the height, the greater the pressure. This high-pressure water enters the powerhouse at incredible force, often exceeding 100 psi, pushing with massive energy. Some penstocks are as wide as subway tunnels and run several kilometers through mountainsides. They're made of reinforced steel to withstand the immense water pressure. At the bottom of the penstock lies the turbine, the workhorse of hydroelectricity. As water crashes into the turbine blades, it causes them to spin, just like a water wheel. These blades are part of a rotor, which is connected to a generator above. There are different types of turbines depending on water volume and head height. Francis turbines are the most common and highly efficient. Pelton turbines are used for high-head, low-flow systems. Kaplan turbines work well for low-head, high-flow rivers. Each turbine is massive. Some weigh over 100 tons and spin at hundreds of revolutions per minute. Every rotation turns mechanical energy into electrical energy through the generator. Attached to the spinning turbine is the generator, the part that actually produces electricity. Inside, magnets spin around coils of copper wire. This motion creates an electromagnetic field, which generates alternating current, AC electricity. The amount of electricity depends on how fast the turbine spins and how strong the magnetic field is. In large dams, each generator can produce hundreds of megawatts on its own. The electricity then travels through step-up transformers, which increase the voltage for efficient transmission across long distances. Once generated, the electricity is sent through high-voltage transmission lines from remote dam sites to towns, cities, and industries across the region. It passes through substations that reduce voltage to usable levels before reaching homes and businesses. Hydropower accounts for over 60% of all renewable electricity worldwide, making it the largest source of renewable energy on Earth. Countries like Norway, Canada, Brazil, and New Zealand rely heavily on hydro to power their national grids. Some hydroelectric facilities use a special system called pumped storage. It works like a rechargeable battery. During low demand periods, electricity is used to pump water uphill from a lower reservoir to a higher one. Later, when electricity demand peaks, the stored water is released back down to generate power again. This system is essential for balancing the grid, storing energy from wind or solar, and ensuring stability. Pumped storage plants can respond in seconds, making them ideal for backup and peak load times. Not all hydropower comes from giant dams. Small-scale hydro projects can power a single community or factory. Micro-hydro systems can power a remote cabin using a natural stream. These systems often have no reservoir, meaning minimal environmental impact. They're popular in mountainous and rural regions where rivers flow year-round. Installation costs are lower, and they offer sustainable power with little maintenance. While hydroelectricity is renewable and carbon-free, it's not impact-free. Large dams can flood ecosystems, displace communities, and block fish migration. That's why many new projects focus on fish ladders, sediment management, and run-of-the-river designs. Modern hydropower aims for eco-friendly integration, working with natural cycles instead of against them. Many older dams are also being retrofitted with fish-friendly turbines and smarter control systems. Balancing energy needs with environmental protection remains a challenge, but one that's being actively addressed. As the world shifts toward renewables, hydropower will continue to play a key role. New innovations like subsea turbines, gravitational storage, and digital grid integration are redefining what's possible. Floating solar panels on reservoirs are also being explored, combining two clean technologies in one location. Hydroelectric power isn't just about energy, it's about infrastructure, environment, and innovation. It powers our homes, our industries, and increasingly, our future. From the silent force of falling water to the roar of spinning turbines, hydroelectric power is one of humanity's most brilliant uses of nature's strength. Efficient, clean, and endlessly renewable, it's a pillar of global energy that continues to evolve. Thanks for watching. This is how millions of kilowatts of water energy are harvested and turned into light, heat, and life. Stay tuned for more incredible journeys inside the world of industrial innovation. Every day, millions of machines quietly keep the world running. Electric cars, elevators, washing machines, industrial robots. At the core of nearly all of them lies a single essential component: the electric motor. But what powers the motor itself? How is it made, and where do the raw materials come from? In this documentary, we step inside a state-of-the-art facility to uncover the full journey, from recycled metal scraps to precision-engineered electric motors. It's a story of molten metal, spinning copper coils, cutting-edge robotics, and sustainable innovation. You'll witness how scrap metal is recovered, melted down, and reshaped, and how advanced manufacturing techniques transform these raw elements into the motors that drive modern life. This isn't just about engineering, it's about the future of power, production, and the circular economy. This is the incredible manufacturing process of electric motors and the metal recycling revolution behind it. Every electric motor begins its life not on an assembly line, but in the scrapyard. Tons of discarded metal, from old appliances, demolished vehicles, and industrial waste, arrive at recycling centers every day. What once was broken and forgotten is now seen as raw material for the next generation of machines. The first step is sorting. Using powerful magnets, conveyor systems, and infrared scanners, metal is separated by type: ferrous from non-ferrous, steel from aluminum, and copper from brass. Precision is critical. Even a small impurity can affect performance in later stages. Once sorted, the metals are cleaned of dirt, oil, and coatings. Then they're shredded into smaller fragments and sent to furnaces where they're melted down. Aluminum melts at around 660 degrees Celsius, copper at over 1000 degrees, and steel at an even higher temperature. Inside the massive induction furnaces, the scrap metal becomes molten, glowing with intense orange heat. Impurities rise to the surface and are skimmed off as slag, leaving behind purified metal, ready to be reborn. The molten metal is cast into standardized forms: rods, sheets, or billets, depending on the motor component it's destined to become. Aluminum may be rolled into housings, copper into winding wire, and steel into rotor shafts. Before these materials even reach the motor assembly line, they've already been through fire, force, and filtration. It's a transformation few see, but one that underpins every step of modern manufacturing. The journey from junkyard to high-performance component has only just begun. At the center of every electric motor are two vital components, the stator and the rotor. Together, they form the beating heart of the machine, converting electrical energy into mechanical motion with remarkable efficiency. Once the raw materials have been purified and shaped, they move into the precision engineering phase, where each part is carefully manufactured to tight tolerances. Let's begin with the stator, the stationary part of the motor. It typically consists of laminated steel sheets stacked together to form a hollow cylinder. These sheets are stamped with slots that will later house copper windings. Lamination is crucial. By stacking thin layers instead of using a single block of metal, the motor reduces energy loss caused by eddy currents, improving overall efficiency. The stator core is placed in an automated winding machine. Here, insulated copper wire, usually made from 99.99% pure recycled copper, is wound into tight, uniform coils that fit into the slots. These coils are not randomly wound, they follow a precise configuration based on the motor's design. Whether it's a three-phase industrial motor or a small DC motor for a household appliance, the winding pattern defines how the magnetic field will be generated. After winding, the coils are dipped or sprayed with varnish, then baked in industrial ovens. This insulation process ensures that the wires remain fixed and protected from moisture, vibration, and heat during operation. Next comes the rotor, the rotating part of the motor. Depending on the type of motor, it may consist of solid steel shafts, laminated cores, or even cast aluminum squirrel cage designs. In induction motors, for example, molten aluminum is injected into molds around a rotor core, forming conductive bars that interact with the magnetic field from the stator. Balancing is critical at this stage. The rotor must spin at thousands of revolutions per minute without wobbling. High-precision machines check for even the smallest imbalance. If necessary, micro-adjustments are made by shaving material or adding weights to achieve perfect symmetry. Bearings are then installed on each end of the rotor shaft. These reduce friction and allow smooth rotation while also handling the mechanical loads during operation. Depending on the application, the bearings might be sealed, ceramic, or even magnetic for ultra-low resistance performance. Once the stator and rotor are completed, they undergo separate quality control inspections. Electrical tests check for coil resistance, insulation integrity, and potential short circuits. Mechanical tests verify alignment, dimensional accuracy, and overall structural soundness. It's only when both components pass all tests that they move to the assembly phase, where the motor will finally take shape. Building stators and rotors is not just about metal and wire. It's about precision, durability, and an invisible choreography of electromagnetic forces. Because inside every electric motor lies a symphony of motion, and it all starts with these two elements, engineered to perfection. With the stator and rotor meticulously prepared, it's time to bring the electric motor to life. The assembly process begins in a clean, organized line where each component is carefully fitted together. The stator is mounted into the motor housing, a protective shell made of cast aluminum or steel, often die-cast from recycled metal. Next, the rotor is gently inserted into the center of the stator, ensuring a precise air gap between the two. This tiny space, measured in fractions of a millimeter, is critical for the motor's efficiency and torque output. Once aligned, end bells, bearing caps, and cooling fans are installed. In larger motors, sensors are embedded to monitor temperature, vibration, and performance in real time. Now comes the moment of truth, testing. Each assembled motor undergoes a series of rigorous quality control checks. First, it's powered on and run through various speed and load conditions. Engineers monitor electrical consumption, heat buildup, and vibration levels. Any irregularities, such as excess noise or current imbalance, trigger a full diagnostic. For motors used in sensitive environments like aerospace or medical devices, testing becomes even more intense. Motors may be subjected to simulated environments, high altitudes, extreme temperatures, or continuous 24-hour runs to validate durability. Only motors that meet or exceed performance standards move on to final packaging. Those that fail are flagged, disassembled, and either corrected or recycled. Every motor that leaves the line is tagged with a serial number and logged in a database for traceability. Whether it's destined for a factory floor, an electric scooter, or a wind turbine, one thing is clear. Its journey from scrap to spinning power is nothing short of extraordinary. Every factory generates waste: offcuts of aluminum, worn-out copper wire, broken bearings, and defective components. But in modern manufacturing, waste is no longer the end of the line. It's the beginning of something new. Metal recycling is not a side process. It's a central pillar of sustainable industry. In the electric motor factory, a dedicated section is designed solely for collecting and processing metallic byproducts. The process begins with collection. Every scrap, from a trimmed copper wire to a rejected steel shaft, is sorted and deposited into labeled bins. Workers and machines collaborate to separate materials with precision. Copper, aluminum, and steel are never mixed. Even slight contamination can compromise the integrity of recycled alloys. To speed up sorting, advanced detection systems are used. Induction sensors, X-ray fluorescence, XRF scanners, and automated vision tools identify metals based on density, conductivity, and chemical composition. These high-tech systems reduce error and maximize recovery. Once sorted, the metals are prepared for shredding. Large industrial shredders chew through hardened parts and tangled wires with ease, breaking them down into uniform chunks. The goal isn't just reduction, it's surface area. The smaller the pieces, the easier it is to melt and purify them later. After shredding, magnetic separators remove any ferrous contaminants from non-magnetic metals. Then eddy current separators isolate aluminum, and density-based systems sift out copper. The result is a clean, sorted stream of valuable raw material, ready for resmelting. But recycling doesn't stop at sorting and melting. Inside the furnace, these metals undergo a second transformation. Recycled copper is refined to 99.99% purity, good enough for electrical-grade wire. Aluminum is cast into ingots or extruded into new housing components. Steel is alloyed and rolled back into rotor shafts and fasteners. The energy required to recycle metal is a fraction of what it takes to mine and process virgin ore. Recycling copper, for example, uses up to 85% less energy than mining. That translates into lower emissions, reduced environmental impact, and more sustainable production overall. What's more, metals can be recycled infinitely without losing their core properties. Unlike plastic or paper, which degrade over time, copper, steel, and aluminum retain their strength, conductivity, and resilience through countless cycles. This circular approach turns the factory into a closed-loop system. The waste of today becomes the resource of tomorrow. Scraps are reborn as stators, rotors, casings, and eventually, as fully functional motors powering the next generation of devices. Recycling also protects supply chains from raw material shortages. As global demand for electric motors grows, driven by electric vehicles, renewable energy, and automation, reliable access to copper and rare metals becomes crucial. Recycling helps bridge the gap. It's not just good economics, it's smart engineering, and a powerful way to align manufacturing with environmental responsibility. In the end, every spinning motor tells a deeper story, not only of precision mechanics, but of a cycle that keeps resources in motion, just like the rotor it powers. At the heart of metal recycling lies one of the oldest and most awe-inspiring processes in human industry: melting. In this chapter, we enter the fiery core of the factory, where scrap metal is reborn in furnaces hotter than volcanoes. Once sorted and shredded, metals are sent to their respective smelting stations. Each type of metal requires different treatment. Copper is melted in induction furnaces that reach over 1,100 degrees Celsius. Aluminum melts at around 660 degrees Celsius, while steel demands temperatures exceeding 1,500 degrees Celsius. These furnaces are no ordinary ovens. Using electromagnetic induction, massive coils generate high-frequency currents that heat the metal rapidly and evenly. Inside, the shredded pieces glow and liquefy, forming a swirling pool of molten metal. But before this liquid metal can be reused, it must be purified. Impurities, known as slag, float to the top of the molten bath. These can include oxides, dirt, old coatings, and traces of other metals. Operators add fluxes, such as borax or limestone, which bond with the impurities and help them separate more easily. The slag is skimmed off the surface and collected for further treatment or safe disposal. For metals like copper, further electrolytic refining may follow. In this process, an electric current passes through a copper solution, causing pure copper to deposit onto cathode plates while impurities fall away. The result is copper so pure it can be used in the finest electrical components. Once purified, the molten metal is ready to take shape again. It's poured into molds, either to form ingots, rods, billets, or sheets, depending on its intended use. Aluminum may be cast into large blocks for machining into motor housings. Copper may be extruded into long wire rods that will later be drawn and insulated for motor windings. Steel is often cast into billets, then sent to rolling mills where it's shaped into shafts, laminations, or fasteners used in motor assemblies. Throughout this process, temperature, viscosity, and cooling rates are tightly monitored. Too hot, and the metal might develop cracks during cooling. Too cold, and it may not flow into molds properly. Precision ensures structural integrity, electrical performance, and long-term durability. After cooling, the solidified forms are trimmed, cleaned, and inspected. Automated scanners check for defects. Some pieces are sent for machining, while others go directly into inventory. It's remarkable to think, these glowing rivers of liquid metal were once tangled wires, broken tools, and crushed devices. Through heat and chemistry, they've been returned to their elemental form, ready for a second life. This stage of the process is more than metallurgy. It's industrial transformation, a demonstration of how science, energy, and ingenuity can give waste a new beginning. From slag to strength, from scrap to structure, each drop of molten metal tells a story of renewal. And every ingot leaving the furnace is one step closer to becoming something powerful. An electric motor built not from mined ore, but from the ingenuity of sustainable design. If you've enjoyed this deep dive into the world of electric motors and metal recycling, there's more where that came from. Here on our channel, we explore the hidden systems that keep the modern world running. Factories that turn scrap into gold, machines that assemble themselves, and the brilliant technologies shaping a more sustainable future. Every process we show is more than just mechanics. It's a story of innovation, precision, and the people behind the scenes who make it all possible. So if you're curious about how things are made, how waste becomes resource, and how industries are being reinvented, hit that subscribe button now. Don't forget to tap the bell icon too. That way, you'll never miss a new episode when it drops. Your subscription helps us keep creating high-quality, in-depth documentaries. Free to watch, ad-friendly, and made for curious minds like yours.